My name is Hipparchus. I lived in the 2nd century before the birth of Christ, and I don't think I'd be bragging if I told you that I am the father of the sciences of geography and astronomy. You know, I wrote more than 14 books, but unfortunately they have almost all been lost in the mists of time. I was responsible for the first catalog of the stars, founded the field of mathematics called trigonometry, and even invented the astrolabe. Fortunately, my brilliant successor, Ptolemy, 3 centuries after my time, inspired by my work, took up where I left off. And nowadays, historians sometimes can't determine what was my contribution and what was his. Ptolemy's manuscript, the Almagest, was the first scientific treatise on astronomy, and his book, Geography, contains the first map of the known world. Geography and geometry both deal with the study of the Earth. Geography is concerned with making visual representations of the Earth, whilst geometry is concerned with measuring it. The shape of the Earth is roughly spherical. Let's forget for the moment that it's slightly flattened at the poles and pretend that it really is a perfect sphere. You probably know, too, that all the points of the sphere are at the same distance from its center. The arrow that you can see now, starting at the center of the sphere and ending at a point moving on the surface, has a constant length. Let's choose an axis for our sphere, a line through the center. When we cut the sphere along a plane that contains this axis, we carve out a great circle, which divides the sphere into 2 hemispheres. If we chop the sphere up using some sort of guillotine that slices down this axis, we trace out the meridian. These are half circles going from the North Pole to the South Pole of the Earth. And now, if we slice the sphere up along a plane at right angles to the axis, we get a bunch of circles called parallels. So now our sphere is covered by 2 networks of curves, the meridians and the parallels. One of these parallels should be very familiar. It's the equator, halfway between the 2 poles. For historical reasons, one of these meridians was chosen to be the principal meridian. It's the one passing through the Greenwich Observatory in England. To specify the position of a point on the Earth's surface, we can start at the point where the Greenwich meridian meets the equator and walk around the equator a distance measured by an angle called the longitude. Colored red. Then you go up along a meridian some way, measured by an angle called the latitude, colored green. finally arriving at our desired destination. Any point on the Earth is precisely described by just these two numbers, its latitude and its longitude. Since we need two numbers to specify a location on the surface of the Earth, we say that the sphere is two-dimensional, and mathematicians often call it S2. Finally, if we let our little plane leave the Earth and fly off into space, then to locate it, we need to give three numbers: latitude, longitude, and the altitude above the Earth. Since we now need three numbers to say where we are in outer space, we say that space is three-dimensional. Look at the paintings on the wall. There's a portrait of Ptolemy, the father of map-making. How do we draw the Earth? One method is to project it onto a plane. Let's choose a city, Dakar, for example. We draw a straight line from the North Pole through Dakar. Our line hits the table at some point that we call its projection onto the table. Any point on the Earth's surface can be projected onto the table in this way. The closer our town is to the North Pole, the farther away its projection on the table is. In fact, it can even end up off the table. For this reason, we say that the North Pole doesn't have a projection. Or, more correctly, that its projection is at infinity. The whole Earth, with the exception of the North Pole, can be represented on the plane of the table. This map of the world is called stereographic projection. Of course, our stereographic projection doesn't preserve sizes. South America appears tiny compared to North America. To get a better idea of what this projection does, we'll roll the Earth along, just like a giant ball. And we'll always project from the highest point. The projections of the continents waltz around in the plane, taking turns at becoming bigger and smaller. But if we take a closer look, we see that shapes don't change, even if lengths do. For this reason, we say that stereographic projection is conformal. What happens to the meridians and the parallels under the projection? When we project from the North Pole, the meridians become radii emanating from the South Pole. And the parallels, concentric circles. And as the Earth turns, you see that both the meridians and parallels always project to either circles or straight lines. Stereographic projection transforms circles drawn on the sphere into circles drawn on the plane. Except for those circles passing through the pole from which we project, whose projections are in fact straight lines in the plane. Now here's our rolling Earth from below. From this point of view, we see the meridians and parallels form two bundles of circles. All of the meridians converge at 2 points, the North and the South Pole. Recognize this one here? Yes, it's the Greenwich Meridian, the end of the first stage of our journey towards the fourth dimension. Now it's my turn to show you around the geometry garden. My name is Escher, and I was a Dutch artist in the 20th century. Geometry was a constant source of inspiration for me. I'm a past master in the art of drawing fantastic tilings. Look at this self-portrait in a spherical mirror. One of my most famous drawings shows lizards drawn on a plane that managed to break out of the paper. Now, perched on high, they contemplate their previous existence as flat life. To prepare ourselves for life in 4 dimensions, we are going to use the ideas behind both my engraving and a little book published at the end of the 19th century by Edwin Abbott, an English clergyman, called Flatland. Let's try to explain to these flat beings, these creatures live trapped forever in a plane, what our everyday life in 3 dimensions is like. Let's imagine that one of these lizards manages to escape his miserable existence for a moment and climbs out and up onto a viewpoint looking down on his world. How would he explain to his fellow reptiles the existence of objects in 3 dimensions? As a first attempt, he could try to pass some 3-dimensional objects through his flat world. Here, for example, is a tetrahedron with its 4 faces passing through the lizard's plane. The flat creatures see a green triangle appear suddenly, then gradually shrink away. This is all they see, since their senses are entirely restricted and they cannot perceive anything outside of their plane. Each time that the lizards see these green polygons appear, change shape, and disappear again, they might imagine the form of the object that has just crossed their plane. To see how hard it is to visualize the form of a geometric body from its cross-sections, try to guess what is crossing through the plane now. A tetrahedron. And now, it was a cube. Of course, you have to remember that these lizards don't have the same perspective we have. All they see is a sequence of polygons, and they'll have to develop an understanding of depth in order to fully appreciate the shape of the body. And now what? An octahedron with its 8 faces. And an icosahedron. It's a solid with 20 faces. And finally, the dodecahedron, 12 faces, 20 vertices, and 30 edges. Now we're going to show you some cross-sections, and only cross-sections, and you have to guess the polyhedron hiding behind them. That was a tetrahedron. That was a cube. It's getting hard, isn't it? You see now that these creatures stuck in 2 dimensions have to develop good geometric intuition if they want to understand something of the 3rd dimension that we take for granted. We'll have just the same kind of problems to get a feeling for the 4th dimension. Here's a 2nd method to explain polyhedra to our flat friend. Start by inflating a polyhedron so that the vertices and the edges are on the surface of a sphere. Then we stereographically project onto the plane of the lizards so that our two-dimensional friends may enjoy the spectacle. Of course, we can spin the sphere around, and with it, our tetrahedron, just as we did before with the Earth. Let's take a look at the cube and see how many vertices, edges, and faces it had. And now, here comes an octahedron. You see the 8 colored faces? Look how the projections of the edges are arcs of circles. Now here comes an icosahedron. Its structure is more complicated, but it's not hard to understand, even for the lizards. One can see 20 faces, 12 vertices, and 30 edges. Can you count them all? Finally, here's a little geometric jewel, the dodecahedron. Now for some exercises. Let's take ourselves down into 2 dimensions and try to recognize the polyhedra from their stereographic projection. It's easy, isn't it? You can see the 4 faces, 6 edges, and 4 vertices. There. It's a tetrahedron. Now, what's this one? 6 faces, each with 4 edges. That's right, it's a cube. That was harder, wasn't it? The faces are triangles. 5 edges start out at each vertex. There are a lot of faces, perhaps 20. It's an icosahedron. Well done. Let's look at the dodecahedron. Each face is a pentagon. If we count them, there are 12 faces. 3 edges start at each vertex. These 5 solids have always fascinated geometers. The Greek philosophers attributed a magical importance to them by associating one of the fundamental elements from which the world is formed to each of them. We call these figures the Platonic solids. So we agree then. It's not easy to get a feeling for the third dimension when you are flat. There is more than one way to do this, but our stereographic projection gives a good idea of what's going on. Now, let's get ready for the fourth dimension. Prepare your imagination for a workout. My name is Ludwig Schleffli. I am a Swiss geometer. I lived during the 19th century, and I'm going to open the door to the fourth dimension for you. Even if I say so myself, I was a visionary. I was one of the very first to understand that spaces with many dimensions really exist, and that their geometry can be studied. If flat creatures living in a plane can understand three-dimensional polyhedra, then why shouldn't we understand polyhedra in 4 dimensions? One of my main achievements was to describe all regular polyhedra in 4 dimensions. What is the 4th dimension? A lot has been written on the subject. Science fiction writers never tire of talking about it. I'm going to explain things on the blackboard. You'll see that this blackboard has a bit of magic about it. What's important is to prepare yourself to forget about the world which is familiar to us and to imagine a new world that our eyes and our senses have no direct access to. We'll have to be smart, just like the lizards were before. I'm going to climb up to a viewpoint that, unfortunately, you cannot see. And I'll try to describe what I see from there. But before we begin, I'll draw a straight line on the board. Let me just mark the origin here. Each point on this line can be located by its distance from the origin, with a minus sign if it's on the left, or a plus sign if it's on the right. Usually the number is denoted by x and is called the abscissa. Since the position of a point on a line can be described by a single number, we say that the line has 1 dimension. Now I draw a second axis perpendicular to the first one. Each point in the blackboard plane is now completely described by 2 numbers. usually denoted x and y, the abscissa, and the ordinate. The plane has 2 dimensions. If you had to explain to some being living on a line what it is to be a point in the plane that is unknown to him, you could simply say, a point in the plane is just a pair of numbers. Let's go to the 3rd dimension. The chalk now writes in the air and draws a 3rd axis, perpendicular to the 2 previous ones. A point in space is described by 3 numbers, x, y, and z. One could say to the reptiles that are curious to know about our world, a point in space is just 3 numbers. Let's go to the 4th dimension. One could try to draw a 4th axis perpendicular to the others, but that's impossible. So we have to do something else instead. Of course, we might just say that a point in the 4th dimension is nothing other than 4 numbers. X, Y, Z, T. That doesn't help us a lot. In spite of the difficulties, we are going to try to get a feeling for this geometry. As a first attempt at understanding, we shall proceed by analogy. Here is a segment and an equilateral triangle and finally a regular tetrahedron. Our magical blackboard enables us to draw in space. How can we keep this up in 4 dimensions? Observe that the segment, the triangle, and the tetrahedron have 2, 3, and 4 vertices respectively. Therefore, we can try to continue with 5 vertices. Let's go then. For the segment, the triangle, or the tetrahedron, an edge connects each pair of vertices. So we have to connect the 5 vertices in pairs. We count 1 edge, 2, 3, 4, 5, 6, 7, 8, 9, and 10 edges. In the tetrahedron, there is a triangular face for each triple of vertices. We proceed the same way, which gives us 2, 3, 10 faces. But if we keep going, by analogy, we have to add a tetrahedral face for each set of 4 vertices. There are 5 sets. That's it. We've constructed our 4-dimensional object. We'll call this the simplex. Let's spin it around in space a little, as we did with the tetrahedron. Of course, you have to imagine the simplex spinning in a 4-dimensional space. What you see is only its projection on the blackboard. What makes things a bit complicated is that faces get tangled and that they cross each other. Well, some experience is required to be able to see in 4 dimensions. We're going to take the simplex, which is in 4D space, and move it gradually so that different cross-sections of it meet our 3-dimensional space. In the same way that reptiles could see a polygon appearing and disappearing, we'll see a 3-dimensional polyhedron which appears, changes shape, and then vanishes. Here is the simplex passing through our 3-dimensional space. We're now going to meet more 4-dimensional polyhedra passing through our own 3-dimensional world. Here's the hypercube, a member of the family that starts with the segment and continues up through the square and the cube. I must confess that getting a feeling for the geometry from the slice method like this is rather tricky. I discovered the analogs of the icosahedron and the dodecahedron. They have complicated names, but I'll just call them 120 cell and 600 cell, since the former has 120 faces and the latter 600. Look at the 120 cell. It's just passing through our space. And now, here's the 600 cell. Of course, when I say that a four-dimensional polyhedron has 600 faces, I mean three-dimensional faces. Yes, these 600 faces are 600 tetrahedra. As for the 120 cell, it consists of 120 dodecahedra. In a minute, we'll see how we can get to know them better. To observe these four-dimensional objects with our three-dimensional eyes, we can look at their shadows. The objects are still in 4D space, but they are projected onto our 3D space, exactly like a painter might project a landscape onto his canvas. We've already done just this with the simplex. Here is the hypercube. Of course, it's spinning in space, so that we can appreciate all the details. Notice, for instance, that the hypercube has 16 vertices. Here's a little newcomer. It's the most beautiful of my discoveries. An object that I call the 24 cell. It has absolutely no analog in 3 dimensions. It's a purely 4-dimensional creature. I am very proud of my discovery. Look how wonderful it is. 24 vertices, 96 edges, 96 triangles, and 24 octahedra. A real little gem. Here's the shadow of the 120 cell in all its majesty. A rather complicated majesty, you have to agree. Let's get inside and have a look at its structure. Look. "600 vertices, 1,200 edges. 4 edges start at each vertex. A completely regular structure. All vertices, all edges play the same role. It's a pity that the projection breaks the symmetry. Let's work your imagination a little. Imagine the object in 4D space where a huge group of rotations permutes all these vertices and edges. The champion is the 600 cell. Like a gigantic macromolecule with its 720 edges and 120 vertices, and 12 edges starting from each vertex. Our exploration of four-dimensional polyhedra won't stop here, as their stereographic projections are bound to give us a better feeling for their geometry. The S2 sphere sits in three-dimensional space, even though it's two-dimensional. In the same way, we can study the sphere in four-dimensional space. It contains all the points that are at the same distance from a center point. But now, to determine the position of a point on this sphere, we need three numbers. This means that the sphere has three dimensions, and so we'll call it S3. You won't be able to see this sphere in four-dimensional space because your space has only three dimensions, and the screen only has two. I can only call upon your imagination. To get a better understanding of four-dimensional polyhedra, we can do just what the lizards did with the three-dimensional polyhedra. We first inflate them so that they lie on a sphere, and then project this stereographically onto the plane. This time we'll inflate the polyhedron until its faces lie on a hypersphere in 4D space, and project stereographically back into our own 3D space. I'm going up to the North Pole of the sphere in 4D space, and I'll project it down to you in your 3D space. You can't see where I am. Just remember how the lizards couldn't see their kinsman up on his perch either. Now we're in exactly the same situation. Here's the simplex. You can see its 5 vertices and its 10 edges. Of course, in this view, edges are circular arcs. So now we have a situation like that of the three-dimensional polyhedra projected stereographically onto a plane. Here's the hypercube. It's easy to recognize it from its 32 edges and 16 vertices. Seeing things this way is so much easier than with the shadow method or the three-dimensional cross-sections. Here's the 24 cell with 24 vertices and 96 edges. Finally, the 120 cell. and the 600 cell. Let's add the two-dimensional faces to get an even better view. The simplex, with its 10 triangular faces. Of course, these two-dimensional faces are pieces of spheres, just as before when we saw that the edges were circular arcs. The simplex is spinning in 4D space before being projected stereographically. Remember when the Earth was spinning like a ball and we saw the motion of the continents? Now and again, a face passes through the projection pole, and its projection becomes infinite. It looks like it blows up on the screen. Let's take a quick look at the hypercube. You see that space is divided into 8 cube-shaped zones. These are the three-dimensional faces of the hypercube. As for the two-dimensional faces, they are squares, though rather bloated and twisted. There are 24 of them. Ah, my favorite, the 24 cell. Look at that. The 24 cell's gorgeous. 24 vertices, 96 edges, 96 triangles, and 24 octahedra. 8 edges start at each vertex. Here's the 120 cell. Let's try to understand its geometry better. Four edges start at each vertex. The two-dimensional faces are pentagons. There are 720 of them. These 720 pentagons form 120 dodecahedra. Look at all those dodecahedra fitting nicely together. Aren't they amazing? Let's finish with the 600 cell with its 600 three-dimensional tetrahedral faces, its 1200 triangular faces, its 720 edges, and its 120 vertices. You can take my word for it, this object has 14,400 symmetries. Well, there you are. We're done with our first voyage into the fourth dimension. It's a dimension full of amazing things. Of course, the mathematician's imagination isn't limited to the fourth dimension. There are the fifth, the sixth, the nth dimension, and even the infinite dimension. Each dimension has its own character, but if you ask me, the fourth is the prettiest. Why? Maybe because, after all, it has a sort of physical reality. Einstein's relativity theory, dating from the early 20th century, binds space and time together into a 4D space-time. A point in space-time is an event, characterized by its position in space, x, y, z, and by the time, t, when it occurs. Relativistic physics, therefore, requires an understanding of four-dimensional geometry. It's interesting to notice that the discovery of this four-dimensional geometry precedes by some 50 years the discovery of relativity. It's one of the many interactions between mathematics and physics that the history of science delights in. I'm Adrien Duadi. My entire life's work in mathematics was centered on the complex number. My contributions helped advance both algebraic geometry and the theory of dynamical systems. Complex numbers have a long history. You see here, on the left, Tartaglia and Cardano, mathematical pioneers who lived during the Renaissance. On the right, Cauchy and Gauss, who consolidated the theory in the 19th century. Complex numbers are not really as complicated as the name might lead you to believe. At first, they were called impossible numbers. Even today, they are still sometimes called imaginary. Well, it's true, it does take a little imagination, yet today these numbers are everywhere in science and are not really mysterious anymore. In particular, thanks to them, one can construct beautiful fractal sets, something I worked on a lot. I even produced a film, The Dynamics of the Rabbit. It was one of the first animated films in mathematics. Let me begin by explaining the complex numbers on the blackboard. Mathematicians just love writing with chalk. You'll see in a minute that my ruler, t-square, and protractor behave rather oddly sometimes. Let's draw a graduated line on the blackboard. One of the most beautiful ideas in mathematics is to link geometry to algebra. This is the starting point of algebraic geometry. Just as we can add numbers, we can add points. Here is a red point on the line and another blue one. Let's add these 2 points. We get the green point. 1 plus 2 equals 3. When the red and blue point move, the green point, which is their sum, must move too. More interesting still is multiplication of points. Let's look at multiplication by -2, for instance. It transforms the point 1 into the point -2, of course. And if you multiply once again by -2, you have to do the same thing. Change sides with respect to the origin, and double the distance from the origin. You get 4, of course. If we multiply twice by -2, we have multiplied by 4. Multiplying by -1 is very easy. Each point is sent to the symmetrical point with respect to the origin. In other words, we do a half turn. A rotation by 180 degrees, if you like. When we multiply a number by itself, the result is always positive. For instance, if we multiply by -1, we make half a turn, so that if we do it one more time, well, we come back to the initial point. This is why -1 times -1 equals +1, simple enough. You see, for instance, that multiplication by -1 sends 2 to -2, and that if you multiply one more time by -1, you come back to 2. Obvious, isn't it? Therefore, there is no number which, multiplied by itself, yields -1. Another way of saying this is that -1 has no square root. But of course, we are underestimating the inventiveness of mathematicians. At the beginning of the 19th century, Robert Argand had a really great idea. He said to himself, since multiplying by -1 is a 180-degree rotation, its square root is a rotation by 1/2 of 180 degrees, 90 degrees. If I do 2 quarter turns, one after another, I end up doing a half turn. The square of a quarter turn is a half turn, hence -1. It's easy when you know how. Argand decided, therefore, that the square root of -1 is the point where 1 ends up after a 90-degree rotation. But of course, this forces us to leave our horizontal straight line, since we just agreed to assign a number to a point that's not on the line. Because this construction is a bit strange, we call this point, the square root of -1, an imaginary number, and label it I. But once we have the courage to leave the line, everything else is easy. We can represent 2i, 3i, and so on. Each point in the plane represents a complex number, and conversely, each complex number defines a point in the plane. Points in the plane become numbers in their own right. These numbers can be added, just like usual numbers. Look at the red point, which is the point 1 plus 2i. Let's add 3 plus I, which is the blue point. Well, you add them just as school children do, giving 4 plus 3i. Geometrically, this is just addition of vectors. You see that it's no problem to add complex numbers. Much more interestingly, these complex numbers can also be multiplied, just like real numbers. Let's see. We know how to multiply a complex number by 2, for instance. 2 times 1 plus I gives 2 plus 2i. Geometrically, multiplying by 2 is easy. It's just scaling up by a factor of 2. If we double the red point, we get the green point. Multiplying by I is not difficult either, since we know that I corresponds to a quarter turn. In order to multiply 3 plus I by I, we just have to rotate by a quarter turn. We get -1 plus 3i. Not so complicated, these complex numbers. And finally, we can multiply any two complex numbers with no problem whatsoever. Let's try, for instance, to multiply 2 plus 1.5i and -1 plus 2.4i. We proceed as usual. We first multiply by 2, and then by 1.5i. Then we add the results. Therefore, we get -2 plus 4.8i minus 1.5i plus 3.6i times I. But recall that I squared is -1, since we invented I for this purpose. This gives us -2 minus 3.6, etc. Let's clean up a bit. We find -2 minus 3.6 plus 4.8i minus 1.5i. That's -5.6 plus 3.3i. There you are. We know how to multiply complex numbers. In other words, we can multiply points in a plane. Amazing. We thought that the plane was two-dimensional, since two numbers are necessary to locate a point. And now, I'm telling you that one number is enough. Of course, we changed our numbers, and are now dealing with complex numbers. Now's a good time to define two notions, the modulus and the argument of a complex number. The modulus of a complex number z is just the distance from the origin to the point that represents z in the plane. Let's use the ruler to determine the modulus of the red point, which is 2 plus 1.5i. Let's see, it measures 2.5. The modulus of 2 plus 1.5i is therefore 2.5. For the blue point, I get 2.6. And for the green point, which is the product of the 2 points, I get 6.5. What's the rule? The modulus of a product of two complex numbers is just the product of the moduli of the two numbers. The argument of a complex number is measured by the angle between the abscissa axis and the straight line joining the origin to the point. Here, for instance, the argument of the red complex number is 36.8 degrees. The argument of the blue point is 112.6 degrees. And for the product, the green point, we get 149.4 degrees. This is the sum of the arguments of the two numbers. When we multiply two complex numbers, moduli are multiplied and arguments are added. Let's finish up our first encounter with complex numbers with stereographic projection. Consider a sphere tangent to the board at the origin. Using stereographic projection, each point on the board, that is, each complex number, corresponds to a point on the sphere. Only the sphere's north pole, the pole from which I'm projecting, has no complex number associated to it. We say that it corresponds to infinity. Therefore, mathematicians say that the sphere is a complex projective line. Why line? Because one needs only one number to describe its points. Why complex? Because this number is complex. Why projective? Because we added a point at infinity using the projection. Aren't mathematicians strange when they try to tell us that the sphere is a straight line? I'm going to show you some transformations. Transforming what? Well, if you don't mind, we'll transform my portrait. Let's begin with something simple. The transformation z goes to z over 2. Each point on the photo corresponds to a complex number z that's divided by 2. We get another point, its image by the transformation, hence a new picture. You see, no surprise, I just shrank to half my size, since each z has been divided by 2. This transformation is called a dilation. How about the multiplication by I? Easy. We know that multiplying by I is just a quarter turn. Note that the modulus doesn't change, but the argument increases by 90 degrees. Indeed, this is quite a sophisticated way of saying that we just rotated the picture. Well, a bit more complicated. Multiplication by 1 plus I. Look at the complex number 1 plus I, corresponding to the point with abscissa 1 and ordinate 1. Its argument is 45 degrees, and its modulus is the square root of 2, using the Pythagorean theorem. Hence, multiplication by 1 plus I amounts to first multiplying its modulus by the square root of 2, and then adding 45 degrees to the argument. In simple words, you have to combine a dilation and a rotation. This is called a similarity. More interesting. We are going to transform the points z into their squares, z times z. Let's begin by placing the photo in a suitable place, flush against the coordinate axes. Then I zoom a little bit since the squaring process will change the size of things, and I need enough space to show you this. Okay, now we can transform the photo progressively. Notice that the argument of z squared is twice the argument of z, so that the right angle on the lower left of the photo is doubled under the transformation. It's turned into a 180-degree angle. Let me place this photo somewhere else, and let's look again at the same transformation, z squared. You'll notice again the same argument doubling. Look, for instance, at my index finger. Before the transformation, its argument is about 45 degrees. And after the transformation, it points upward at 90 degrees. But you can also observe that moduli are squared. Now let's go to a new transformation, sending the point z to negative 1 over z. Don't forget, with complex numbers one can add, multiply, but also divide. Not by 0, of course. Doesn't this image remind you of the Sistine Chapel? Large complex numbers with large modulus become small when one takes their inverses. And conversely. Here is a similar transformation. Look at the formula. The value of k changes slowly. Some parts are expanded, others are contracted. But if one looks closely, the shape is preserved, even though lengths are not. A circle remains circular, even though it might grow. My hand grew, my face became smaller, but you can still recognize me. One more transformation, more involved. Well, this one's not really a weight loss program for me. But note once more that even though I got bigger, the shape of small parts did not change. If you look, for instance, at a button on my shirt, it keeps a circular shape. We say that these transformations are conformal or holomorphic. Rather complicated Latin and Greek words for saying that they preserve shapes. Indeed, with complex numbers, you can do quite a lot. You can even take the exponential, if you know what this means. But even if you don't know, look at the treatment I have to suffer from the exponential. Has my head disappeared? No. If you look through a microscope near the origin, you could see my beard. Now that you know about complex numbers and have seen some transformations, I'll explain some of the objects I've been studying. Here you see a number of points, Some are blue, inside the unit disk, and some are yellow, outside. Let's perform the transformation z squared several times and look at the result. You can see that the blue points stay inside the disk, while the yellow points escape from the disk, and even escape from the screen. We say that the blue disk is the filled-in Julia set of the transformation z squared. Points outside the Julia set escape to infinity when one repeats the transformation indefinitely. But we can play the same game with other transformations, like, for instance, those of the form z squared plus c, where c is a complex number that we will choose at will. For each complex number c, we get a Julia set whose shape changes when c changes. You can see a few examples here. Here's the one I called the rabbit. In order to understand how these shapes change, I'll show you several things in parallel. On the left side, the red side, you can see a point that will start to move. This is the point C. On the right side, you see the corresponding Julia set. It's deforming as C slowly changes. But sometimes, for some values of C, the Julia set seems to disappear, and we can't see anything on the screen anymore. Like now, for instance. The truth is that the Julia set blew up into an infinite number of pieces so small that you don't see anything on the screen. Benoit Mandelbrot, who popularized fractal sets, suggested the study of this set drawn in red that describes the values of C for which one can see the Julia set clearly on the screen. In other words, those for which the Julia set does not blow up into multiple pieces. Of course, this red set is called the Mandelbrot set, and I spent quite a lot of time studying it. To finish, let's look closely, very closely, at this Mandelbrot set and zoom inside so you can appreciate how beautiful it is. Let's go. Here it is. Admire. For once, I won't explain everything. Imagine the Mandelbrot set as a black island surrounded by a tropical sea, and that you can see the bottom of it. Really, you're looking at truly microscopic details. If the Mandelbrot set were the size of a soccer field, we'd be looking at details the size of a single atom, on the order of a millionth of a millimeter. Maybe you're wondering why I got interested in this. First of all, because it's beautiful, and because understanding these objects gave me much pleasure. For me, this is reason enough to spend time on these questions. But also, because in these transformations that look so simple, we can find the essence of chaos, such a fundamental concept in modern science. Simple things generating rich structures. To study complicated phenomena through their simplest incarnation, this is often the role of the mathematician. Circles in space, arranged to create beautiful ornaments. In order to better understand the three-dimensional sphere in four-dimensional space, I'm going to show you how to fill space with circles and thus create what mathematicians call a fibration. By the way, my name is Heinz Hopf, and I'm one of the main contributors to the development of topology during the first half of the 20th century. Look at this torus, filled with circles that appear to be linked. Let me explain this picture to you. Circles, spheres, and tori are among the simplest objects studied by topologists. A topologist tries to understand the connections between these objects. I worked in Berlin, Princeton, and Zurich, and one still comes across my name often in contemporary mathematics. Poincare-Hopf theorem, Hopf invariant, Hopf algebra, Hopf fibration. Let me paint my portrait for you. I published the discovery of my fibration in 1931. But, as always, I have to say that I relied upon many predecessors, like Clifford, for instance, whom you see here, and who worked in England during the 19th century. Let's begin with some explanations on a blackboard. Well, a whiteboard this time. What do you see? A two-dimensional plane? Well, yes and no. This is indeed a two-dimensional plane, but it's a plane with two complex dimensions, or in other words, a space with four real dimensions. Give it a try. Each point in this plane is determined by two coordinates, but each of these two coordinates is a complex number, which, remember, is itself defined by two real numbers. Each of the axes is a complex line, so each point on a given axis has one coordinate which is a complex number. For instance, here you see the point 2 minus I on the first axis. The same is true for the other axis, the y-axis. Here we can see the point 1 minus 2i on this axis. Now, our whiteboard is magical. Now our whiteboard is magical, but not enough to be able to show us the two planes simultaneously. If we try to depict them in three-dimensional space, they will intersect along a line. But in four-dimensional space, they intersect only at the origin. After all, they are axes. Now what do you see? A circle? Yes and no. What you see, or rather, what you should imagine, is the set of points in four-dimensional space that are a distance 1 from the origin. In other words, this is nothing other than the three-sphere, S3. Well, of course, you need to have a little imagination. Let's try to see at least how this sphere intersects the first axis. The three-sphere intersects the first axis in the set of points on this axis which are at a distance 1 from the origin. You see, the three-sphere intersects the first axis in a circle. The same is true for the second axis, which intersects the three-sphere in a circle as well, the blue circle. Now, what is true for the horizontal line and the vertical line is equally true for all lines going through the origin. Here you can see the line with equation z2 equals -2 times z1. But we could do the same with any line, z2 equals a times z1, for any complex number a. In this manner, the three-sphere in four-dimensional space is filled with circles. One for each complex line through the origin in our plane of two complex dimensions. Careful, though. In the picture, you get the impression that the red circles intersect each other. But this is not the case in the four-dimensional reality. Lines meet only at the origin, so their intersections with the unit sphere don't intersect at all, in fact. I discovered some very interesting things about this decomposition of the sphere into circles, and ever since it is known as the Hopf fibration. Why fibration? Well, you could think of the fibers of fabric. We are going to look at all that using stereographic projection. Imagine that we project the three-sphere from the North Pole onto the tangent space at the South Pole, which is our three-dimensional space. Here is the projection of one of the circles, which, as we have seen, is the intersection of one complex line and the three-sphere. But there are many such circles, one for each complex line going through the origin. For each complex number a, we can consider the line z2 equals a times z1 and its associated circle. Let's vary this number a, or what will amount to the same thing. Let's rotate this line in order to see how the circle changes. Notice that sometimes the circle appears to be a straight line, but this is simply because it passes through the North Pole of our three-sphere. Let's look at two of these circles simultaneously. In the lower left-hand corner, you see two moving complex points, one red, the other green. You can see the circles associated to the red and green points. Note that these two circles are linked together like two links of a chain. It is impossible to separate them without breaking them. Just for the fun of it, let's consider three circles. See how the three linked circles dance together? Now let's take many more complex lines, chosen randomly, and let's look at them all at once. The circles fill space, and no two of them intersect. This is an example of a fibration. Let's try to understand this better by returning to the board for a moment. Look, we have a Hopf circle for each line. Each one of these lines has an equation of the form z2 equals a times z1, where a is a complex number, the slope of the line, and is indicated by the red point moving on the green line. Actually, the vertical axis does not have such an equation, but in this case, we may say that a is infinite. Don't forget that a is a complex number. The green line is also a complex line, so it's a real plane, of course. Summing up, the complex lines that we are interested in are completely determined by a point on the green line and an additional point at infinity. But we already saw that if we add a point at infinity to the complex line, we get the usual two-sphere. Once more, this is stereographic projection. So, the complex lines that interest us are parametrized by points on the yellow sphere, the two-dimensional sphere S2. So we have a circle for each point on the two-sphere. But a circle is a one-dimensional sphere, isn't it? All these circles fill up the three-sphere. Each point on the three-sphere belongs to a single circle and therefore defines a point on the two-sphere. In this way, we get a projection from the three-sphere to the two-sphere. Complicated, isn't it? Mathematicians say that above any point of the base, S2, there is a fiber, which is a circle, S1, and that the total space of this fibration is the sphere, S3. I am very proud of my fibration, all the more so because it has become a fundamental object in topology. Let's come back to the two-dimensional sphere and its parallels. Above each point of the two-dimensional sphere, we should imagine a Hopf circle. Look at what's above one of the parallels of S2, the equator, for instance. Here's what's above another parallel, which is moving southwards. Why does the torus seem to get thinner? Because above the South Pole, there's, of course, only one circle. And above the North Pole, you see a straight line. Actually, a circle going through infinity. This is the red line. Well, let's spin all this around now. Rotations, yes, but rotations in four-dimensional space, of course. To be honest, I must admit that some of these pictures were already known long before me. The existence of four families of circles on the torus is usually attributed to the Marquis de Villarceau. But one finds earlier clues in a sculpture in the Strasbourg Cathedral, for instance. Take a torus of revolution. This is the surface described by a circle rotating around an axis in its plane. Slice the torus with a plane. Notice how I chose the plane. One says that it is bitangent to the torus, simply because it is tangent at 2 points. Now, look carefully. Plane cuts the torus along two perfect circles. This is Villarceau's theorem. A plane, which is bitangent to the torus, cuts it along two circles. Of course, there's not just one bitangent plane. Here's another one, cutting the torus along two other Villarceau circles. And we can do the same for all other bitangent planes. We just need to rotate around the axis of symmetry. You see, through each point on a torus of revolution, we can draw 4 circles obtained by suitable slices. One of these circles is a parallel. Another is a meridian. Then a first Villarceau circle. And a second one. And since one can do this at any point of the torus, we see that the torus is covered by 4 families of circles. 2 circles of the same family do not intersect. A blue circle intersects a red circle in a single point. A yellow circle and a white circle intersect in 2 points. These are the Villarceau circles. Take a good look at the yellow circles. These are Hopf circles. Remember when we looked at what is above a parallel in the fibration? We saw a torus covered with linked circles, just like this torus covered with yellow circles. And what about the white circle? Well, they are the fibers of another Hopf fibration, the mirror image of the first one. To finish our stroll, we'll take a torus of revolution with its 4 families of circles. Imagine it in the 3-dimensional sphere. Rotate the torus inside the 3-dimensional sphere, and finally, project it stereographically onto 3-dimensional space. In this way, we obtain surfaces that are also covered by 4 families of circles, the so-called Dupin cyclides. Sometimes when the torus passes through the projection pole, the surface becomes infinite. In this movement, the two faces can even be switched. The inner face of the torus is pink, and the outer one is green. A simple rotation in the fourth dimension, and bingo, green turns into pink, and pink into green. Isn't that magnificent? Doing mathematics means, above all, proving what one claims. We've seen that stereographic projection sends circles on the sphere not going through the pole to circles in the plane. And now, we're going to prove it. Even though this has been known for many centuries, it is I, Bernhard Riemann, who will present this proof to you. I'm frequently honored because one speaks today of the Riemann sphere. Proving is much more than showing. It's not enough to see in a movie that some curve looks like a circle to be sure that it is indeed a circle. A mathematical proof must use reasoning to be convincing and must explain why it is indeed a circle. The great Euclid, during the 3rd century before Christ, formulated the rules of the mathematical game in his book, The Elements. A proof has to rely on facts that, themselves have to be proved. But one has to start with something, so that some statements have to be accepted without proof. These are the axioms. Therefore, mathematics appears as a gigantic construction whose foundation consists of the axioms, and such that each brick rests on the previous ones. In order to prove the theorem about the stereographic projection of circles, we should in principle start with the axioms. Of course, we have no time for that now. We'll assume we already know the theorems of geometry that are often studied in high school, and we'll prove this theorem. Start with something simple: the intersection of a sphere and a plane. We see that if a plane cuts a sphere, and if it is not tangent to the sphere, then the intersection is a circle. We can see it, but why is it true? How do we prove it? Let's consider an arbitrary plane colored in blue. We can draw the perpendicular from the center C of the sphere to the plane. Let's call P the foot of this perpendicular. Consider 2 points, A and B, on the intersection of the sphere and the plane. And let's look at the 2 triangles, CPA and CPB. They share a common side, CP. Both have a right angle, since the angle at P is of course a right angle, since the plane is perpendicular to CP. But note that the hypotenuses, AC and BC, have the same length because A and B are on the sphere and thus sit at the same distance from the center C. But recall the Pythagorean theorem. Since our 2 right triangles have 2 sides of the same length, their 3 sides have the same length. Hence we've proved that PA and PB have the same length. That is, that A and B are on the same circle with center P in the blue plane. Therefore, we proved that all points which are both on the sphere and the plane belong to some circle. Does that imply that all points on this circle are on the sphere and on the plane? A priori, no. We still have to prove it. Let A be a point which is on the sphere and the plane. Consider the circle in the blue plane with center P and that goes through A. We'll prove that this circle is contained in the sphere. Let B be some point on that circle. Look at the 2 triangles CPA and CPB. They share a side, CP. Both are right-angle triangles since the angle at P is a right angle. But the lengths of PA and PB are equal since A and B lie on the same circle with center P. Again, using the Pythagorean theorem, we conclude that the hypotenuses have the same length. CA equals CB. This means that the point B also lies on the sphere, since it sits at the same distance from C as A. That's it. We've proved that when a plane cuts a sphere, the cross-section is a circle. Let's look now at a diameter APB of our circle, and let's place it in the plane of the screen. The blue plane appears as a straight line on the screen, and the sphere appears as a circle. Let's draw the tangents to the circle at A and B. They intersect in a point S. Of course, the line CS is again a symmetry axis for our figure. Why? Well, because the triangles CAS and CBS are equal. Why? Well, because they are both right-angled triangles having a common hypotenuse, and the sides CA and CB have the same length. Why? Well, because these are two radii, of course. You see, if we had to go to the end of all the arguments, this film would be the longest in movie history. Look, we proved that any circle drawn on a sphere can always be thought of as the contact locus between a cone of revolution and a tangent sphere. If you like, the sphere is like ice cream in a cone. Well, we shouldn't forget what our aim is, to show that stereographic projection carries circles onto circles. Let's first prove what mathematicians call a lemma. Here is the tangent plane to the sphere at some point A, seen from the side. Now, here is the tangent plane at some other point B, and also seen from the side. These two planes intersect along a line D, but presently we see only one point since this line is perpendicular to the screen. The figure that you're looking at is symmetric with respect to the bisecting line of the two lines that we see. This three-dimensional picture is symmetric with respect to the bisecting plane of the two tangent planes. Choose some plane containing the segment AB. It intersects the line D in a point M, unless it is parallel to D, of course. The figure's symmetry with respect to the bisecting plane shows that AM and BM have the same length. The triangle ABM is isosceles. Voila! That was our lemma. Now we can prove our theorem using what we just learned. Consider a circle on the sphere which does not go through the North Pole. We want to show that its projection is a circle. Look, if instead of projecting onto the tangent plane to the South Pole, we projected onto some other parallel plane, the famous theorem of Thales would imply that all the projections are similar. Hence, in order to prove our theorem, we may choose the projection plane as we wish, as long as it is parallel to the tangent plane to the South Pole, of course. So let's place our yellow circle in a cone. Remember, the ball of ice cream in a cone with vertex S. Well, we are going to project onto the horizontal plane through S. The point B projects onto a point D. But look at the figure. The triangles AMB and DSB are similar. Why? Well, again, Thales' theorem. Do you agree? Now, remember our lemma. The triangle ABM is isosceles. Hence, the same is true for the triangle BDS, so that BS has the same length as DS. When B moves along the yellow circle, the segment BS stays tangent to the sphere. Its length, therefore, remains constant. Since BS and DS have the same length, the moving segment DS also maintains a constant length. Let's see. Saying that DS has a constant length means precisely that D describes a circle with center S, so that the projection of our yellow circle on the horizontal plane through S is contained in a circle. We have seen that by Thales' theorem, this implies that the projection on the tangent plane to the south pole is also contained in a circle. And this is what we wanted to prove.
What you're looking at right now is something called quaternion multiplication. Or rather, you're looking at a certain representation of a specific motion happening on a four-dimensional sphere being represented in our three-dimensional space, one which you'll understand by the end of this video. Quaternions are an absolutely fascinating and often underappreciated number system from math. Just as complex numbers are a two-dimensional extension of the real numbers, quaternions are a four-dimensional extension of complex numbers. But they're not just playful mathematical shenanigans. They have a surprisingly pragmatic utility for describing rotation in 3 dimensions, and even for quantum mechanics. The story of their discovery is also quite famous in math. The Irish mathematician William Rowan Hamilton spent much of his life seeking a 3-dimensional number system, analogous to the complex numbers. And as the story goes, his son would ask him every morning whether or not he had figured out how to divide triples, and he would always say, "No, not yet." But on October 16, 1843, while crossing the Broom Bridge in Dublin, he realized, with a supposed flash of insight, that what he needed was not to add a single dimension to the complex numbers, but to add 2 more imaginary dimensions. 3 imaginary dimensions describing space, and the real numbers, sitting perpendicular to that in some kind of 4th dimension. He carved the crucial equation describing these 3 imaginary units into the bridge, which today bears a plaque in his honor showing that equation. Now, you have to understand, our modern notion of vectors with their dot product and the cross product and things like that didn't really exist in Hamilton's time, at least not in a standardized form. So after his discovery, he